Assalamu alaikum. It is for my great pleasure and delight to contribute to this important conference on Kalam and related matters. My talk will be concentrating on a philosophical question, in fact, in the philosophy of quantum mechanics and in Kalam, in the philosophy of Ilmul Kalam, specifically in those topics related to natural philosophy. Mutakallimun devised the notion of recreation of accidents, that is, the properties of natural objects, within their atomic theory on theological basis. The notion stands as one of the fundamental principles of their Daqiq al-Kalam, which deals with the topic of natural philosophy. An extensive analysis of the principles of Daqiq al-Kalam has been given in my book entitled Daqiq al-Kalam, The Islamic Approach to Natural Philosophy. I find that the principle of recreation can be utilized efficiently to solve one of the most fundamental problems in theoretical physics, that is the problem of quantum measurements. In this talk, I will analyze this problem and show that the principle of recreation can provide us better explanation of the quantum phenomena and can provide us with the new predictions in quantum mechanics. The new explanation resolves the discrepancies between the wave properties of particles and the particle properties of waves, elaborates the controversy about the applicability of quantum mechanics to single particle systems and the ensemble of particles, explaining at the same time the statistical nature of quantum mechanics. I will start with a short introduction about quantum mechanics in order for the people to understand what I'm talking about. Quantum mechanics is the best theory which can explain the natural phenomena in the microscopic world. Quantum measurement is the backbone of applied quantum mechanics. However, it is a common understanding among physicists that understanding quantum measurement is still a problem that requires a solution in order to clarify the deep implications of quantum theory. There is no consensus among physicists about this. Instead, they have different views and interpretations regarding how quantum measurement can be interpreted. Physicists now can do without agreed interpretation, by the way. They don't need to agree on any interpretation. Since for practical purposes, they only need the mathematical tool of quantum mechanics to perform calculations and then test it by experiment. That's what they normally do. But for further development of quantum mechanics, we really need to understand the problem of measurement much more deeper than we have now. And we need to resolve the problem. In this talk, I present a new interpretation of quantum mechanics based on the notion of continued recreation of physical properties of the systems. This principle of recreation is I borrowed it from Kalam on the conceptual level. And here I am not going to go through mathematical details since we are discussing the subject in the context of the philosophy of science and Kalam physics. I will try to foresee some of the implications of this interpretation in physics and biology, and I also will glance upon some philosophical and theological implications. Early development of quantum theory. The most fundamental notion of the early quantum mechanics was based on observations that particles behave like waves. The main difficulty in realizing the wave-like description for particles lays in the fact that particles are localized, whereas waves are extended. This problem was overcome by Louis de Broglie in 1924 with his suggestion that a particle, a moving particle, can be represented by a plane wave, which has the wavelength inversely proportional to its momentum. This notion was soon realized to obtain a description of particles in terms of the de Broglie, or what's called the de Broglie wave packets, with the wavelength of the packet being that of the group of waves rather than one single wave, a group of waves representing the particle. This description opened the way to formulating classical localized particle mechanics in terms of wave mechanics. Accordingly, the wave equation derived by Erwin Schrödinger in 1926 to describe the time development of atomic particles under any field force was formulated. The wave mechanical description of particles set by Schrödinger was best realized by saying that a particle is a wave packet, which is composed of superposing many basic elementary plane waves. This description soon led to describe the physical system in terms of a sum of all possible states available. Here we should note that the states are not all equally probable. Rather, the probability to find the system in one state depends on how frequent that state recurs. This has established the probabilistic nature of physical systems. And because we do not know beforehand in which state the system will reside at any particular time, physicists realized that quantum systems are indeterministic. The mathematical structure of quantum mechanics is based on the representation of physical systems as waves, or wave functions rather. This is designated by the symbol psi, which is a mathematical description for the system. Any value for the physical properties of the system can be obtained through applying the corresponding mathematical operator on that wave function. But as the system can be found in different states, we expect to have different possible values for the same physical observables, though being under the same physical conditions. The fact that the calculations of quantum mechanics have predictive power that can be verified experimentally makes the mathematical structure and methodology very attractive and trustful, even though such formulation lack convincing interpretations. However, there are several questions that find no answer within the available interpretations. Some of these important questions are: first, does quantum mechanics apply to microscopic systems only, or is it applicable to macroscopic systems too? Is there a border between the microscopic and the macroscopic worlds? Second, does the superposition principle represent a factual, ontological representation of reality, or does it arise as a fictitious epistemological artifact of the wave mechanical representation of the physical system? Third, how can quantum indeterminism be understood in the physical context? And fourth, how can we explain quantum entanglement, taking into consideration that it appears like a spooky action at a distance as described by Albert Einstein? The founders of quantum mechanics tried to resolve the questions regarding how the system being in the superposition state could jump into a given state upon measurement by saying that the wave function of the system collapses to one of the possible states when performing or upon performing the measurement. This interpretation was introduced by Niels Bohr and Heisenberg in what is known now the Copenhagen School. But this interpretation introduces the role of the observer into the measurement, therefore implying that our consciousness, our own consciousness, determines the state of the system. This interpretation may imply that superposition state is a factual ontological state, despite that we do not realize it consciously. Erwin Schrödinger cynically criticized such an interpretation, objecting to the ontological status of the superposition state by his famous cat paradox, the Schrödinger cat. In fact, there have been several interpretations of quantum mechanics other than the Copenhagen interpretation, I should say. I will not go through this, as I said. I would rather go through my suggestion with the recreation proposal. I set two postulates, two assumptions. Postulate one says all physical observables, that is the measurable properties of any physical system, are subject to continued recreation, very fast recreation. Postulate 2 says the frequency of recreation is proportional to the total energy of the system. The first postulate will imply that the observables of a physical system are generally multivalued. In each recreation cycle, the physical observable can have new value. This explains the multi-state spectrum of the physical system. These states will be discrete, and the distinction between them will depend on the rate of recreation. The second postulate would imply that the system possessing high energy content will have high recreation rate, high recreation frequency, which implies narrow width of the states. This means that the classical systems, for classical systems, the macroscopic systems, will practically have a continuous spectrum. The second postulate can be quantitatively formalized by the relation that F, the recreation frequency, equals the total energy E of the system divided by H, the Planck constant. Now we need to explain the quantum phenomena. I do not claim that I have a full-fledged theory of recreation, but I can see that this proposal can be developed to produce rigorous explanations for virtually all the quantum phenomena. First, the probabilistic nature of quantum system is now understood because the system is naturally under continuous change at a rate defined by the recreation frequency. For a free system, there is where the external potential is zero, the value of the observables follow the normal statistical distribution. The width of this distribution depends on the recreation frequency. The higher the recreation frequency, the narrower is the spectral band for that observable. Thus, the observable is therefore expected to take values near to the initial value possessed upon the first creation. That is to say, it depends on the initial conditions. The nearer the value of a given observable to its initial value, the higher is its probability. Second, many other quantum phenomena can be explained using this proposal. For example, the double-slit experiment can be explained by saying that the electron is truly passing through the two slits simultaneously during the available time of measurement. Calculations shows that this is indeed the case for realistic systems. Practically, when we enlarge the distance between the two slits, the interference pattern disappears. The electron has no time to pass through the two slits simultaneously. Tunneling effect, quantum entanglement, the quantum Zeno effect, and many other phenomena can also be explained with the same approach. Biological evolution can also be addressed using the recreation proposal. Several events in genetical evolution can be studied, and many questions can be answered in this respect. I'm not a biologist, but I have read some of the reviews about rigorous treatment of the question of adaptive mutation and random mutation, and I can see that the recreation principle would contribute positively to solve many problems in this respect. As for the theological questions, perhaps the most important question here is the one related to divine action and the relationship between the creator and the created. This would now be understood through the continuous recreation or the continuous connection between the recreator and the created, which is established through this process of continuous recreation. In the eyes of Allah, God, everything is determined, but in our eyes, the world is indeterministic. This is because Allah, or God, is the creator and He is the recreator. We cannot determine what value for an observable to be recreated at any one time. We can only calculate the physical value and the probability for each observable. But no one can tell when such value will occur upon measurement. This is what physicists admit. They admit that nobody can tell us when a specific value would certainly occur. The recreation proposal is very promising indeed, and I hope that researchers in theology departments and the departments of Kalam would pay attention to the wealth embodied in the basic principles of Daqiq al-Kalam, to utilize them in resolving problems in theology and follow a new rational approach to construct a new Kalam. In fact, at this age, we need to reconstruct Kalam in a new approach. Bases are available, well qualified to play indeed a very, very important role in the contemporary philosophy of science. That is why I encourage researchers, PhD students, to consider many problems that we can propose for studies and to give, in order to give solutions for such problems in philosophy of science, in philosophy of modern science, and in theology too. And I will stop here.